Right off the coast of Northern California, Oregon, and Washington, something is happening beneath the ocean floor that scientists have never been able to directly observe anywhere on Earth before now. A tectonic plate is actively tearing itself apart in real time as it dives underneath the North American continent. And I want you to picture this correctly, because it's not the dramatic movie version where a plate suddenly splits clean in half in one violent moment. It's slower and, honestly, stranger than that. It's tearing itself into pieces one section at a time, almost like a train coming off the rails car by car instead of derailing all at once. And, as if that discovery wasn't enough on its own, in that exact same stretch of ocean floor, a completely separate team of researchers just confirmed something else entirely. They found a chunk of ancient seafloor that vanished from the geological record roughly 30 million years ago, a piece of crust that scientists assumed was long gone, and it has just resurfaced in the data, sitting directly beneath one of the most seismically dangerous junctions in the entire country. Two separate peer-reviewed discoveries, published only months apart from each other, and together they are forcing scientists to redraw the map of exactly what is moving beneath the Pacific Northwest coastline. So let's slow down and break this apart properly. What was actually confirmed, what it really means for earthquake risk in this region, and why this picture just got significantly more complicated than almost anyone in the field expected. Before we get into the discoveries themselves, you need to understand the basic geography of what we're even talking about, because none of this will make sense without it. Off the coast of the Pacific Northwest sits what's known as the Cascadia subduction zone. This is a stretch of plate boundary that runs from Cape Mendocino in Northern California, all the way north to Vancouver Island in British Columbia. Along this boundary, you have two oceanic plates, the Juan de Fuca plate and its smaller southern neighbor, the Gorda plate, and both of them are being forced underneath the much larger North American plate in a process geologists call subduction. Here's the thing, though. Neither of these plates is actually a complete original tectonic plate. Both the Juan de Fuca plate and the Gorda plate are remnants, leftover fragments of a much bigger ancient plate called the Farallon plate. At one point in Earth's history, the Farallon plate covered an enormous stretch of the eastern Pacific Ocean, but over tens of millions of years, most of it was consumed as it slid beneath the continent, leaving behind these two comparatively small fragments that are still, to this day, grinding their way underneath North America. And this isn't some minor low-stakes fault system we're talking about here. According to the Pacific Northwest Seismic Network, this exact tectonic system is capable of producing earthquakes at magnitude 9.0 or larger. That's the same category of earthquake that caused the devastating 2011 Tohoku disaster in Japan, the one that triggered the massive tsunami and the Fukushima nuclear crisis. This is the fault system that people refer to when they talk about the Pacific Northwest's own version of the big one. So when scientists start telling you they found new structural complexity buried within the system, that's not a small headline. That matters. Think about the sheer scale of what we're actually discussing here for a moment. The Cascadia subduction zone runs for roughly 700 miles of coastline, cutting through some of the most densely populated and economically important stretches of the entire West Coast. Cities like Seattle, Portland, and countless smaller coastal communities all sit within range of whatever this fault system eventually produces. And unlike a lot of famous fault systems that people are more familiar with, where the two sides of the fault mostly just slide past each other horizontally, subduction zones like Cascadia involve one plate being forced directly underneath another, which is the specific geometry that tends to generate the largest earthquakes on the planet, along with the tsunamis that come attached to them. So every new piece of structural information scientists uncover about this system isn't just an academic curiosity. It's directly relevant to millions of people living within its reach. Now here's where things get genuinely fascinating, because for decades, scientists have operated under the assumption that they had a reasonably complete picture of how these plates behave once they start sinking into the Earth. That assumption just got upended. Using advanced seismic imaging techniques, essentially building a three-dimensional picture of what's happening deep underground by analyzing how seismic waves generated by earthquakes travel through different rock structures at different speeds and angles, researchers were able to directly observe the Juan de Fuca plate splitting into distinct fragments as it descends beneath North America. This finding was published in the journal Science Advances, and it represents the very first time scientists have ever directly observed an active subduction zone breaking apart in this specific manner anywhere on the planet, not inferred from old rock, not reconstructed from ancient geological remnants, directly observed happening right now in real time using modern data. Rather than the plate collapsing all at once in some single catastrophic tearing event, researchers found that the breakup happens in stages, in a process they're calling episodic termination, or piecewise termination. The plate tears apart one section at a time, and for each individual piece to fully detach and break away, the process takes several million years. To help make sense of this, the researchers offered a genuinely useful analogy, and I think it's worth repeating because it clarifies the whole concept immediately. Picture a runaway train. Instead of the entire train crashing all at once in a single pileup, imagine individual cars being cut loose one at a time. Each time a car detaches, the remaining train loses a bit of its momentum. It's a surprisingly intuitive way to think about something that's otherwise happening in total darkness, miles beneath the seafloor, in a place no human being will ever physically witness. Now, apply that same idea to the plate itself. Each time a fragment breaks away and forms what geologists call a microplate, which is just a smaller, independently moving piece of what used to be one single continuous slab, the larger plate loses some of the gravitational pull that had been dragging it downward into the Earth. That loss of pull gradually reduces the overall force driving the entire subduction system forward. And here's the part that really puts this in perspective. Over a long enough timeline, this piece-by-piece breakup can eventually contribute to shutting an entire subduction system down completely. That's not speculation. It's something that has clearly happened elsewhere in Earth's geological history, and this new research actually helps explain some genuinely puzzling features found in other ancient, now abandoned subduction zones around the world, including orphaned tectonic fragments that geologists could never quite account for, and unexplained bursts of ancient volcanic activity that have stumped researchers for years. Now, I want to pause here and be really clear about something, because I think it's incredibly easy to hear the plate is breaking apart and immediately jump to the conclusion that something catastrophic and imminent is unfolding. It isn't, at least not on any timeline that matters to anyone alive today, or frankly, anyone alive for the next several thousand generations. This is a process playing out across millions of years. Columbia University's Climate and Earth Science News publication, which reported on this discovery, specifically emphasized that this breakup is not necessarily bad news in the dramatic way that phrase might initially suggest to someone scrolling past a headline. What this discovery actually represents is scientists finally being able to directly observe, with real, hard data, a process that had previously only ever been inferred indirectly, pieced together from clues left behind in the geological record by ancient subduction zones that vanished long ago. This is a genuine leap forward in scientific understanding of how these systems behave. It is not a countdown clock ticking toward disaster. But here's the thing. That's only half of what's been confirmed recently in this region. And the second discovery is, in a lot of ways, even more significant when you're specifically talking about earthquake hazard, because it's not about a slow, multi-million-year process happening broadly across the whole system. It's about the actual structural complexity sitting directly underneath one of the most dangerous points on the entire West Coast right now. In January of this year, a completely separate team of researchers published new findings in the journal Science. And this study wasn't focused on the broader Cascadia system as a whole. It zoomed in specifically on the Mendocino triple junction, which is the exact point off the coast of Northern California, where three major tectonic plates, the Pacific Plate, the North American Plate, and the Gorda Plate, all converge and meet simultaneously. If you're not familiar with why triple junctions matter so much, as this is widely considered one of the most geologically complex and most seismically active locations anywhere in North America, precisely because you have three separate plates all grinding, interacting, and pushing against each other within the same relatively confined area. It's genuinely one of the messiest spots on the entire tectonic map of the continent. To study this junction, researchers pulled data from thousands of tiny, otherwise completely unremarkable earthquakes. We're talking about quakes so small and so weak that no human being would ever feel a single one of them. But collectively, across thousands of these tiny events, researchers were able to build an entirely new model of what's actually happening beneath this junction. And what they found genuinely surprised even seasoned geologists who have spent their careers studying this exact stretch of coastline. Buried beneath this junction, researchers confirmed the existence of something they're now calling the Pioneer fragment. This is a leftover piece of that same ancient Farallon plate we talked about earlier, a chunk of oceanic crust that geologists had long believed disappeared beneath North America roughly 30 million years ago and had essentially become irrelevant to modern tectonics. Except it hadn't vanished at all. It had simply been sitting there, largely unnoticed, stuck to the floor of the Pacific Ocean this entire time. And now researchers have confirmed it's actively being dragged northwest beneath the continent as the Pacific Plate continues its overall motion, essentially hitching a ride embedded within the seafloor as the larger plate carries it along for the journey. On its own, that discovery would already be significant. A 30-million-year-old fragment of a supposedly extinct plate, quietly riding along beneath one of the most watched fault systems on the planet, completely unaccounted for until now. But researchers identified something else buried in that same dataset. And the second piece may actually be even more important from a pure hazard perspective. A separate fragment, this one broken off from the North American plate itself rather than from the ancient Farallon system, has also detached from the main body of the continent. And it's now sinking downward alongside the Gorda plate as that plate continues to subduct beneath the continent. Put all of that together, and here's what it actually means. Classic geological maps of this region have, for a long time, shown just three simple interacting tectonic plates at this junction. Pacific, North American, Gorda. Clean, straightforward, three moving pieces. Researchers have now confirmed at least 5 separate, independently moving pieces of crust all interacting beneath this one junction. The Pacific plate, the North American plate, the Gorda plate, the newly confirmed Pioneer fragment, and this newly identified detached chunk of the North American plate that's sinking alongside the Gorda slab. 5 pieces where the textbook said 3. And here's exactly why that number matters so much when you're talking about earthquake hazard modeling specifically. Every single additional independently moving piece of crust in a system like this represents another surface where stress can build up over time. It's another boundary where 2 separate pieces of rock can grind against one another and eventually slip, which is, at its core, what an earthquake actually is. And it's another variable that seismic hazard models now have to account for when scientists try to estimate how large a future earthquake in this region could actually be, and exactly where along the fault it might rupture. Think about it this way. A system with 3 simple, well-understood interacting plates is already a complicated puzzle for scientists to model accurately. A system that turns out to actually contain 5 separate moving pieces, 2 of which weren't even confirmed to exist until earlier this year, is a meaningfully more complex puzzle to solve. And every additional piece of that puzzle represents additional uncertainty that scientists now have to work through before hazard models can catch up to what's actually happening underground. It's a little like discovering that a bridge you thought was held up by 3 support beams actually has 5, 2 of which you never knew were even there. The bridge itself hasn't necessarily become less safe overnight, but your understanding of exactly how the load is distributed across it and exactly where the greatest stress is concentrated changes considerably the moment you know the true number of supporting pieces. This isn't purely theoretical, by the way. We already have real-world seismic evidence of exactly this kind of internal complexity playing out in actual earthquakes. Back in December of 2022, a magnitude 6.4 earthquake struck near Ferndale, California, close to this exact same triple junction region. When researchers from the United States Geological Survey later went back and analyzed the seismic and geodetic signatures of that earthquake and its aftershock sequence in careful detail, they found something genuinely revealing. The main shock itself occurred as strike-slip faulting, which is essentially a sideways grinding motion, and critically, it happened within the subducting Gorda slab itself, rather than along the main subduction interface, where the Gorda plate actually meets the North American plate. That detail might sound small, but it matters enormously because it demonstrates directly that the Gorda plate is not behaving like a single, rigid, uniform slab of rock as it subducts beneath the continent. It's a plate that experiences what geologists call significant interplate deformation, meaning it's genuinely breaking and shifting internally, generating its own independent earthquakes purely from stresses building up within the plate itself, separate entirely from the stress building up along the main subduction boundary, where the truly massive, potentially magnitude 9 earthquakes are expected to eventually occur. In other words, the Gorda plate isn't just one clean slab sliding smoothly underground. It's cracking and shifting internally as it goes. And once you accept that even a single subducting plate can behave this unevenly, it becomes a lot easier to understand why researchers went looking for even more hidden structure at the Mendocino junction in the first place, and why they ended up finding exactly that. Researchers studying the Ferndale earthquake sequence also found something else worth mentioning here, because it adds another layer to this whole picture. They documented small but measurable deformation that occurred after the main earthquake, and this deformation was best explained by what's called slow aseismic slip, meaning gradual movement that doesn't produce its own noticeable earthquake, occurring specifically on the main subduction interface, apparently triggered by stress changes generated by the Ferndale rupture itself. What that finding demonstrates is that these different fault systems, the interplate faults within the Gorda slab and the main subduction interface itself, aren't behaving as completely separate independent systems from one another. They're actively interacting. One system's activity is capable of nudging stress onto the other system. And that is exactly the kind of coupled behavior that makes hazard forecasting in this region considerably more complicated than if scientists could simply treat each fault as an isolated, self-contained hazard sitting neatly on its own. There's one more piece of context here that's worth understanding, because it actually extends the significance of all of this research beyond just the immediate Cascadia and Mendocino region. Some existing scientific evidence suggests that a major earthquake along the Cascadia subduction zone could potentially trigger subsequent earthquakes further south along the San Andreas Fault. And if that's true, it would meaningfully widen the geographic footprint of danger beyond what's traditionally been modeled as two largely separate, self-contained fault systems. The San Andreas Fault directly abuts the southern end of the Cascadia subduction zone, right around this same triple junction area, with the Pacific and North American plates grinding past each other in a sideways, transform-style motion along the San Andreas, while just to the north at Cascadia, the Juan de Fuca and Gorda plates are diving directly beneath the continent in a completely different style of tectonic motion altogether. Now that researchers have confirmed this much additional structural complexity, sitting right at the exact junction where these two very different fault systems physically meet, it only reinforces why researchers are increasingly starting to treat this entire region as one single interconnected system, rather than analyzing Cascadia and the San Andreas as though they operate in complete geological isolation from one another. So let's step back for a moment and talk about what all of this actually means in practical real-world terms, because I think it's genuinely important to separate the scientific significance of these discoveries from any implication that something dangerous has suddenly become newly imminent. What's been confirmed here is not evidence that an earthquake is somehow more likely to strike tomorrow than it was last year. That's not what any of this data says. What's actually been confirmed is that the underlying structure of this fault system is meaningfully more complex than the model scientists have been relying on for decades. And that complexity matters enormously, not because it changes the underlying danger, but because it changes the accuracy of long-term hazard assessments, the exact kind of assessments that inform building codes, insurance risk models, and emergency preparedness planning across the entire Pacific Northwest. Every single time, researchers identify an additional moving fragment, an additional zone of internal deformation within a plate that scientists previously modeled as rigid, or additional evidence that separate fault systems are mechanically coupled rather than fully independent from each other, that new information eventually works its way into updated hazard maps and updated probability estimates for how large a future rupture along this coastline could actually turn out to be. None of that happens overnight either. Updating a hazard model that informs building codes and insurance calculations across an entire region is a slow, deliberate process, one that involves cross-checking new findings against decades of existing seismic records before anything official actually changes. But that slow, methodical process is exactly what makes the end result trustworthy, rather than reactive. This is exactly how earthquake science has always progressed. Not through sudden dramatic leaps, but incrementally, through exactly this kind of painstaking analysis of tiny, otherwise unremarkable earthquakes, combined with advanced imaging techniques that simply did not exist a generation ago. And honestly, the fact that scientists are still discovering fundamental new structural features of the Cascadia system in 2025 and 2026, and one of the most extensively studied subduction zones on the entire planet, tells you something genuinely humbling about how much complexity remains buried beneath even our best mapped, most heavily researched fault systems. We like to think of major scientific regions like this as fully understood territory, especially somewhere as heavily monitored, funded, and studied as the west coast of the United States. But this research is a pretty clear reminder that we are still very much in the middle of figuring it out. Even here, even now, even with decades of accumulated data and some of the most advanced imaging technology available anywhere on the planet pointed directly at this coastline. If you live anywhere along the Pacific Northwest coast, whether that's Northern California, up through Oregon and Washington, or into British Columbia, I'd treat this research as a good reminder to make sure your own earthquake preparedness genuinely reflects the well-established risk this region already carries, rather than reacting to headlines suggesting that something has suddenly changed for the worse overnight. Because here's the honest truth of it. The Cascadia subduction zone has been capable of producing a magnitude 9 earthquake for as long as it has existed as a geological system. That fundamental risk has not increased simply because scientists just got better at seeing the structure underlying it. What has genuinely improved is our understanding of exactly how that risk is distributed across the region and exactly how these different fault systems interact with one another. And over time, that improved understanding is what will make emergency planning and building codes more accurately targeted at the specific hazards this region actually faces, rather than relying on an older, simpler model that we now know is missing pieces. None of this is meant to alarm you unnecessarily, but it's also not meant to be brushed off either. The reality is that living in a region capable of a magnitude 9 earthquake means preparedness should already be part of the baseline, independent of whatever the latest research happens to reveal. What research like this does is sharpen the picture, not create the danger from scratch. So if you haven't reviewed your own earthquake preparedness recently, this is genuinely a good moment to actually go do it. Know whether your home has been retrofitted to current seismic standards, particularly if you're living in an older structure that predates modern building codes. Have a basic emergency kit ready with water, food, and medical supplies to last at least several days, since a major Cascadia rupture could disrupt infrastructure and transportation routes across a wide swath of the region simultaneously, unlike a more localized single-fault earthquake that tends to affect a much smaller footprint. And if you live near the coast specifically, make sure you actually know your tsunami evacuation route in advance, because a major rupture along this subduction zone would generate a tsunami with extremely limited warning time for coastal communities sitting closest to the fault itself. In some modeling scenarios, we're talking about a matter of minutes, not hours, between the rupture and the wave reaching shore. I'll keep tracking research coming out of this region closely, because between the confirmed piecewise breakup of the Juan de Fuca plate and the newly identified Pioneer fragment and detached North American chunk sitting beneath the Mendocino triple junction, this is clearly an area of active, rapidly evolving scientific understanding right now. And honestly, I would not be surprised at all to see additional discoveries revise this picture even further within the next year or two. Given how much has already changed in just the last few months alone, it feels almost inevitable that more pieces of this puzzle are still waiting to be found. The moment anything significant comes out of continued research in this region, or if seismic activity here shows any meaningful change tied to what we just walked through, I'll bring you a complete update, explaining exactly what changed and why it matters. Because at the end of the day, this is exactly the kind of confirmed, published geological research worth following closely, not because it means disaster is coming tomorrow, but because it's actively reshaping how scientists understand one of the most dangerous fault systems in North America, in real time, right in front of us. It's also worth remembering just how recent all of the tools behind these discoveries actually are. The kind of seismic imaging that let researchers watch the Juan de Fuca plate splitting into fragments, and the kind of dense earthquake catalog analysis that let a separate team uncover both the Pioneer fragment and the detached chunk of North American crust at the Mendocino junction simply did not exist in any usable form a generation ago. The computing power required to process thousands of tiny earthquakes into a coherent three-dimensional model of the crust is a genuinely modern capability, which means the pace of discovery in a region like this is likely to keep accelerating, not slowing down, as these techniques keep improving and as more data continues to accumulate year over year. Stay curious about what's actually happening beneath your feet, because as this research just proved once again, even the most heavily studied fault systems on the entire planet are still capable of revealing genuine secrets. We are watching the map of the Pacific Northwest coastline get redrawn in real time, piece by piece, discovery by discovery, and that is a genuinely remarkable thing to witness unfold within the span of a single year of published research.